In exercise 4.3, we will combine plots using the ggplot package. So we will have 4 different plots from the previous exercises: the PCA plot, the p-value histogram, the box plots, and line plot, and then combine them with the ggArrange function in a 2x2 grid, and then play around a bit with the different settings. So first, we will recreate all of plots we did before. We have to save them as objects here to use them later. And then we can use the ggArrange function with these 4 plots. And with nrow and ncol2, we will have this 2x2 grid. And if we do that, you can see here that it did basically one plot containing the 4 different plots here. And then different settings are possible. You can play around with the heats and the widths. So in the default setting here, each plot will have the same space, but you can change that, giving here, for example, the ones on the bottom more space and giving the ones on the right side more space. Then we can change the way the legends are done. In this case here, only these 2 have a legend, but they can be combined because they are both about the grouping C versus HCC. So we can do that with common legend true. We can also say where the legend should be at the bottom. In this case, we can have labels. So labels mean that it puts here A, B, C, D on the panels, which is really handy. And we can say that they should align the plots. This basically means that they have the same width or heat. For example, here you can see that the histogram starts here, but the line plot starts here. This is because actually the counts here are larger, so they up to 1000, but here the log2 intensity is only up to 17. So here the labels of the axes need more space than here, so a bit of space here is lost for the plot. And this would look a bit nicer if they are aligned, so if they also start at this point here, the second graph. And this is what you can do with the align function. And HV means that it does this alignment horizontally and vertically. So we can run all that. And yeah, we can perfectly see that now we have more space here for this plot, less space for this plot. We have a common legend, this is here at the bottom. And we have this alignment. You see here that this plot starts here and the D plot that's also here. And we have this ABCD labeling. In exercise 4.4, we will have a look at facet wrap and facet grid. We will do histograms of the log2 transformed intensities, separated for each sample or separated by gender and group. And then we will also have an advanced task that tries to do box plots of 9 proteins with the highest Euclidean distance in the volcano plot. So first we will read in the data set again. So here we will do the histogram, and you see that we use facet wrap and use the name column as a facet. So this will cause actually that we will have multiple plots now in the panel. And each plot is the distribution of the protein intensities in one sample. And you see that we didn't specify any number of rows or columns. So in this case, ggplot will just decide on a reasonable number. So here we have 7 times 6. In the second part, we will use the same, but use facet grid and have the rows as the group and the columns as the gender. So we get a 2x2 panel, and here the distribution is basically the common distribution of all the samples that fall into this category. For example, all females in a control group will have together this distribution. and so on. For the next part, we will do the small box plots of the 9 proteins with the highest Euclidean distance. So we will read in the Volcano data, then we will filter them. So this is where the slice max function comes in handy. So we actually use this to get the highest 9 Euclidean distances. Then we transform the data to long format and separate again the information about the group and patient number. So we actually have then this data frame here, which has here the intensity, the patient number, the group, and only contains the data from the 9 proteins with the highest distances. Then we can use facet wrap on the accession number, so to have separate plots for each protein and to have a 3 times 3 grid, we can use nrow as 3. And you will see here that we use scale 3 to be better visible. I can also show the comparison. So here, if you use scale 3, it basically means the y-axis here, the range is decided for each plot on its own. If we set it to fixed, then this would look like this here. So for some plots you can't really see anything because the range is too high for the data range basically. Because it's then decided on actually this protein here, for example, with the highest variability. So it would be better to have it like this, where you can see actually the differences better.